production is more than 60 million tons per year, including fly ash of 12 million tons per year from 32 coal power generation stations, and the iron and steel slugs, that is slug 1, of 41 million tons per year, including blast furnace slug of 23 million tons per year, and the steel making slug 1 of 80 million tons per year. And garbage melting furnace slags, that is slug 1, that's 2, of 8 million tons per year from 112 garbage disposal plants in 39 prefectures. Almost all of these fly ash and slugs effectively used together with cement in the field of the civil work according to the chemical and mechanical characteristics. The utilization of these fly ash and slugs have led to the reduction of cement and therefore CO2, a contributor to global warming. Further uses of fly ash and slags must be developed. One approach is to develop geopolymer. This lecture introduces method for production of high compressive strength geopolymers, strength diagnosis of geopolymers, and the chemical and mechanical characteristics of geopolymer by mixing fly ash and slags as binders with NaOH and sodium silicate as activators. Table 1 shows chemical compositions of tested geopolymer materials. I prepared totally 24 geopolymer samples, and they are classified 9 categories of geopolymer materials. As chemical compositions, these 6 compositions are shown, and I treated these 3 compositions, SiO2 Al2O3 CaO, as main chemical composition of geopolymer. Figure 1 shows triangular coordinate display for tested geopolymer materials. Triangle is drawn for CaO, SiO2, and Al2O3 plus others. This display method helps us to understand the situation of chemical composition of binders visually. For production of geopolymers, as preparation of binders, the particle size of D50 was smaller than equal to 0.106 millimeter. Refer to Komoto's ASCE paper shown here. For making geopolymer sample, since the compressive strength Qu is considered as a function of W, which is ratio solution NaOH plus sodium silicate to solid binders by weight, and eta, which is ratio of NaOH to sodium silicates by weight. Refer to Komoto's AC paper, Ws equal to 0.4 is used. And here, eta was used in the range of 0 to 1.0. After remolded geopolymer samples were cured at room temperature and curing for 24 days, then used for compression test. Fig 2.1 shows Qu eta relationship for fly ash slag 1 and slag 2. From the figure, for every sample, Qu eta relation generally becomes a curve having a peak value at a certain eta. These peak value and eta value was defined as Qmax and ηopt. Fig 2.2 A and B show Qu eta relationship for acid-proof cement and mixed binder geopolymer samples. From the figure, for every sample, Qu eta relation similarly becomes a curve having peak value at a certain eta. Table 2 shows compression test results of geopolymer materials. In the table, rho T is density of geopolymer sample at Qmax, and delta V by over V is volume shrinkage ratio of geopolymer sample at Qmax. Now we go to discussion. Fig 3 shows relationship between ηopt and each chemical composition of binders. Circle are for SiO2, and the triangle is for Al2O3, and plus mark is for CaO. In the case of Al2O3 and SiO2, ηopt is in proportion to each chemical composition, this one, like this. But in the case of CaO, any OPT is inverse proportion to CaO. Komoto has proposed to use a factor Ccas, which is equal to Al2O3 plus SiO2, and to correlate with ηopt, and has obtained the ηopt equation shown in figure 1 here. Rather high correlation factor. In the present lecture, I propose newly to use a factor Ccas is equal to CaO over Ccas, considering the three main factors in this factor. And the present and correlated with ηopt, and could obtain the ηopt equation and higher correlation factor R equal 0.950, shown in figure 4.2. Using a factor Ccas, some mechanical properties can be characterized well. For example, in figure 5, Qmax characterized as Qmax greater Qmax characterized as Qmax greater than equal to 100 Newton per square millimeters can be obtained when Ccas is in the region of 0.5 to 1.2. And in figure 6, the volume shrinkage ratio, delta V over V, characterized as delta V over V become less than 2% when Ccas is smaller than 0.9. Figure 7 shows triangular coordinates display for geopolymer materials yielding Qmax greater than equal to 100 Newton per square millimeters. This display method also helpful to understand visually the situation of geopolymer materials which yield Qmax greater than equal to 100 Newton per square millimeters. We came to the last discussion. There is an important question as, can Qmax be expressed as a function of chemical compositions of binders? I try to correlate the Qmax with three main chemical compositions of binders: SiO2 power alpha multiply Al2O3 power of beta multiply CaO power gamma in equation 1, as equation 1. Then to obtain the high correlation coefficient for the function by least square method, the values of alpha, beta, and gamma were found by error and trial to be alpha equal 0.67, beta equal 0.67, and the gamma is equal to 1. The Qmax equation obtained is expressed for a high correlation coefficient as equation 2. Qmax is equal to 18.49 exponential 7.67 multiply 10 power minus 4 chi, and where chi is expressed by this. Figure 8 shows the Qmax to chi which is expressed by this. And the equation Qmax obtained by using a least square method by this equation. Figure 9 is comparison of experimented Qmax and estimated Qmax from above mentioned Qmax equation. All data are plotted along the 45 degrees line and included in plus minus 25% lines. Now, conclusions are to produce the high compressive strength geopolymer, slags must be grounded to as fine as possible. And there is optimum value, ηopt, the weight ratio of NaOH to sodium silicate, yielding Qmax for each binder at W equal 0.4. The eta is well correlated with the factor Ccas as this equation. And the value ηopt for an arbitrary binder necessary to manufacture the high compressive strength geopolymers is designed by the above equation. The factor Ccas is effective to diagnose the high compressive strength geopolymers, and the binders having the factor Ccas in the range of 0.5 to 1.2 yields the high compressive strength geopolymers with Qmax being greater than 100 Newton per square meters. The above, the volume shrinkage ratio, delta V over V, is generally less than 2% when Ccas is smaller than 0.9. The Qmax can be estimated by using three main chemical compositions of binders by the